Okay, hi everybody. Welcome back to Calculus 3 class notes. We are on page 65, the last page of our section 14.6 notes, where we're speaking about differentials and linearization of functions of two variables. So, okay, here's a definition about the total differential. If we move from one point, x naught, y naught, to a point, x naught plus dx, y naught plus dy nearby, the resulting change, df, which is the partial of f with respect to x, evaluated x naught, y naught, times dx, plus the partial of f with respect to y, evaluated x naught, y naught, times dx. That, in the linearization of f, is called the total differential of f. Okay, so if you look back in the linearization of f, this point, these two guys right here, okay, so if we're looking at this dx now, is the distance from x naught to the new point. Okay, so up here, we were looking at x minus x naught as trying to write it as an, where we could put x, any point x and y in there. Okay, so the problem with that is when you get here, by the way, this should be y minus y naught. I'm very sorry about that. I just noticed that. This should be y minus y naught right here. Okay. So in any ways, all right, fix that. When you come over here, now we're going that distance dx. So instead of x minus x naught, we're calling that dx. Okay. So but this piece is called the total differential of f. And we can use that just like we used differentials back in Calc 1 again. So for example 61, suppose that a cylindrical can with volume V equals pi r squared h is designed to have a radius of 1 inch and a height of 5 inches, but that the radius and height are off by amounts dr, which is plus 0.03 inches, and dh, which would be minus 0.1 inches. So they made the radius a little too big and the height a little too short. Estimate the resulting absolute change in the volume of the can. So instead of actually finding the change in the volume, we're going to approximate it with dV using differentials. So that would be the derivative of V with respect to R, evaluated R naught H naught, which is what it should be, times dr, which is the change in the radius, plus the partial of V with respect to H, evaluated R naught H naught, which is what we should be, times dH, which is the error that's in the height. So dV then is partial of V with respect to R is 2 pi RH, evaluated at the point 1,5, radius of 1, height of 5, times dr, which is the error that's in the radius, plus pi r squared, the derivative of V with respect to H, right, partial of V with respect to H, pi r squared evaluated at 1,5 times the error in the height. So when I plug in 1 and 2 for R and H, I'm sorry, 1 and 5 for R and H, I get 10 pi times 0.03 is the error that was in the radius. When I plug in 1 for R here, I get pi and times the error in the height, which is minus 0.1. So the error in the volume then can be thought of as multiplying these out and approximating it. So 0.2 pi is approximately 0.63 cubic inches. Now, if I have functions of more than two variables, I can linearize, right? I can linearize my function by just looking at this and saying, okay, I just add this third component. Instead of having this plus f sub x times x minus x naught plus f sub y times y minus y naught, I also have the third component. And similarly in the total differential. Okay, so I can have this third piece of it, partial of f with respect to z times dz. And that gives a good approximation of the resulting change in f. Right? Remember, we're trying to take delta f and approximate it with df. All right, so example 62, find linearization, Lxyz of f of xyz equals x squared minus xy plus 3 sine z at the point x naught, y naught, z naught equals 2, 1, 0. So in other words, we're finding some sort of a hyperplane here, okay? And then we're going to linearize this function with that. So f of 2, 1, 0 is, that's what I'm trying to figure out. This guy right here is just 2. Then I take the gradient of f and I evaluate it at 2, 1, 0. So I get 3 minus 2, 3. Thus, the linearization of this surface, or this hypersurface, because it's a function of 3 variables, you can't really visualize it, is 2 f of p naught, the point we're at, plus the gradient of f, and partial of f with respect to x at 2, 1, 0, which is 3 times x minus x naught, plus partial of f with respect to y at 2, 1, 0, which is minus 2 times y minus y naught, plus partial of f with respect to z at 2, 1, 0 times z minus z naught. I simplify that and I get this guy. And this is a good approximation to f of x, y, z as long as I'm near the point 2, 1, 0. And that ends section 14.6, differentials and linearization of functions.